We started talking about inductance, we started talking about capacitors and then inductors. We did talk about the fact that these are energy storage devices, elements. Today we're going to talk about mutual inductance. Okay, before now we're talking more about self-inductance. So we will be looking at mutual inductance today. When inductance relates a voltage to a time varying current in the same circuit, it is referred to as self-inductance, and that is usually called L. So it's just the inductance. It is related to a voltage in a circuit, a voltage source in a circuit, in a time varying current, because we said that the current cannot be constant, the current cannot be, the ID, the T cannot be zero, and the current cannot be constant. Otherwise, the inductor will just act as a short circuit. So a time varying current in the same circuit, it is usually referred to as a self-inductance. When two circuits are linked by a magnetic field, voltage induced in the second circuit can be related to a time varying current in the first circuit by a parameter called mutual inductance. And that mutual inductance is usually represented using a symbol M. The symbol M. You can see a current source here, and then you can see an inductor here. This is an inductor. You can see this is an inductor, and then this is the second inductor. You can see N1 represents the number of turns for the first inductor, and then N2 represents the number of turns for the second inductor. For the first inductor, you can see there is a voltage V1, and then there is a voltage V2 for the second inductor here. Each of them have is magnetic flux here, magnetic flux 2,1. This is magnetic flux 1,1. I'm going to explain what that means to you. This is another magnetic flux 2,1 here. I'm going to explain what that means to you right now, and then this is magnetic flux 1,1. All right. Dots provide information on the winding in the magnetically coupled coils, especially when the winding mode is not obvious. So linkage formulas can be derived based on Faraday's laws. Using that concept, we can come up with these two expressions here. Now, the most important one that I want us to talk about now is this. V2 is equal to M21 multiplied by the I1 dt. You will find out that V2 is the voltage induced in the second inductor. M21 is the mutual inductance, and I'm going to explain to you what M21 means. What 21 means. The I1 dt, I1 is the current passing through the first inductor. I1 is the current passing through the first inductor. To find V2, we are multiplying this M21. M21 represents the mutual inductance in this second voltage due to the current in the coil 1. Okay, you can see the first two represent mutual inductance as a result of the second voltage, this V2, mutual inductance of this V2 based on the current passing through coil 1. So when current is passing through coil 1, it induces a voltage V2 on coil 2. All right. So the mutual inductance based on the magnetic field between the two coils is what we refer to as M21. I'll take that again. M21 represents the mutual inductance that relates the voltage in the second coil based on the current passing through the first coil. So mutual inductance relating voltage in the second coil, that's why we have two here, second coil, based on the current passing through coil 1, first coil. That is why we have 1 here. So you can also have what we refer to as M12. M12 will represent mutual inductance in the first coil. Mutual inductance relating the voltage in the first coil based on current passing through the second coil. That is what we refer to as M12. Okay, so M12 is always equal to M21. Okay, this is a rule. M21 is always equal to M12, and then you can choose to represent them with just one single M, since they are equal, and that is what is expressed right right here. Okay, for ferromagnetic material, this law is binding. So please pay attention to this. And then your M21, in case we don't know M21 and you want to find it, it is usually given as N2 multiplied by N1 multiplied by P21, where P21 is the permeance of the space occupied by file 21. Permeance of the space occupied by file 21. Okay, then what is file 21? Just like we define M21, your file 21 will be the magnetic flux that relates the voltage in the second coil based on the current passing through coil 1, just as we defined our M21. We have that here. And then we have our P21, and then we have all these equations. Okay, so then you can define your file 1 just like we explained file 2 this is just magnetic flux that relates voltage induced in coil 1 based on current passing through coil 1 with file 1. You can easily define this, and then you can define every other thing here. You can see here we have a circuit, a very important circuit, which is going to be like this represents the first coil. Okay, that's why we have L1 here, the first coil, so the first inductor, and then here we have L2, the second inductor. All right, now the mutual inductance is going to be based on the magnetic field that is between L1 and L2. So we're going to have mutual inductance between the two of them because a magnetic field will be created here. The closer they are, the stronger the magnetic field. The further apart they are, the weaker the magnetic field. Okay, so there is going to be a mutual inductance based on these two inductors that are brought together and the magnetic field that exists in both inductors. We're going to have a mutual inductance here. Now, this mutual inductance, like I mentioned earlier, we're going to have M21, right? M21 is the inductance that relates the voltage in the second coil, voltage in coil 2, which is V2, that relates voltage in coil 2 based on the current in coil 1. This is M21 represents that inductance that relates voltage 2 induced in coil 2 based on current flowing through coil 1. And then we're also going to have M12. M12 will be mutual inductance that relates voltage in coil 1 to the current flowing in coil 2. So, and both of them, since they are supposed to be equal, we can just represent them with just one single M and say M21 equal to M12 equal to M. So how do you find your M when you have a situation like this? You find your M by using this expression, M equal to K square root L1 times L2, where L1 and L2 are the respective inductances of coil 1 and coil 2, and K is usually given as the coefficient of coupling. It has to be greater than or equal to 0 or less than or equal to 1. When K is equal to 1, what does it mean? When we have K equal to 1, we are indirectly saying that there are no losses, okay? It means that the two coils are perfectly coupled together. This is for perfect coupling. Perfect, let me put it here as perfect. So this is perfect coupling when we have K equal to 1. All right. So we are assuming that there are no losses. The inductors are perfectly connected together. They are perfectly linked together, perfectly coupled together. So K will be equal to 1. In that case, there won't be anything here. Your M will just be equal to square root of L1 multiplied by L2. There are times when you can have your K to be greater than 0.5. K can be greater than 0.5. When K is greater than 0.5, what you can assume is you can say they are tightly coupled together. When K is greater than 0.5 but less than 1, they are tightly coupled, together. The first one, K equal to 1, K greater than 5. Then you could have K less than 5, all right? When K is less than 0.5, not less than 5. K less than 0.5 would mean that they are loosely coupled together. So the two inductors are loosely coupled. They are loosely coupled together when they are, so they are loosely coupled together when K is less than 0.5. So these are different scenarios that you can have, for your values of coupling, coefficient of coupling or coupling coefficient. Okay, when there is no flux linkage at all between the coils, M is going to be equal to 0. When there's no flux linkage, like I told you guys, the flux linkage between these two inductors will be depending on the strength of the magnetic field between them. Okay, so that if they are closely connected, it means that the M here will be very high. If they are loosely connected, if they are not close, they are farther apart, M is likely going to just keep tilting towards 0. M is going to, the further they go apart, the more M tends to 0, because the magnetic field between them will be weak and there will not be flux. There will not be many magnetic flux between the coils. As you see here, like I told you guys, the current always come in through the positive end of inductors. So if you have that in mind, so that simply means if the current is this way, this place is supposed to be the positive end, right? And this place is going to be the negative end here. All right, this is going to be the positive end here, because current is coming this way, and this is going to be negative end here. So the current polarity, direction is usually done in such a way that it flows through the positive end of the inductor, except otherwise stated. Dot convention for mutually coupled coils. This is very important. When the current enters the dotted terminal of a coil, it induces voltage with positive polarity at the dotted terminal of the second coil. When current enters dotted terminal of a coil, so this is current entering this coil here. Can you see that? Current is entering this dotted terminal of this coil. It induces voltage with positive polarity. So here, the current coming in here is coming into the positive polarity here, but there will be a voltage here called V2, right? So the V2 here, it will induce positive voltage polarity here. So this will be negative. Can you see that? This is very important, okay? At the dotted terminal of the second coil and vice versa. So current is coming here through the positive end here. This is negative here. All right. So that means here this is positive for this. Here we have positive here. So automatically this is going to be negative here. This is going to be positive here. Do you all understand this convention? This convention is very important. When current enters the dotted terminal of a coil, this is the dotted, this is a dot here. So this is the dotted terminal of this particular coil with inductance L1. So current enters here. It will induce voltage with positive polarity at the dotted terminal of the second coil. This is the dotted terminal of the second coil. So the voltage here, it will induce positive polarity for the voltage here. That's why for V2 we have, this is going to be for V1. So for V2 we are going to have positive here and negative here. And like I told you guys, current is going to be coming in here. So current is going to just come in. Once this is positive here, automatically this is going to be negative, and then current is going to just come in through this other end here. All right. So please pay attention to that. All right. Okay, so current is entering at the dot here. This is positive, this is negative. So this positive and negative here represents the flow of current. All right. So this voltage V1 here is induced by the current I2. That is why I took my time to explain M21 and M12 to you guys. This voltage here is not induced by this current I1. Voltage V1 is induced by current I2. Are you following that? And current I2 has positive and negative here. All right. So whatever sign you have at this dotted point is what will be induced at the opposite end here. All right. So at this dotted point here, we have negative. That means negative will be induced at the dotted end of this voltage V1 here, because V1 is induced by current I2. Do you understand what I'm saying? V2 will be induced by current I1. And that is why if you flip back a little, you will see, I think there was something I showed you guys here. We said M21 will be equal to dI1 dt. V2 is M21 dI1 dt. V2 is induced by current 1, not by current 2. So this is what I'm now talking about. You will find out that here, this is what we have here now is our V2. Okay, so V2 will be equal to M dI1, as you can see. Okay, V2 is M dI1 because V2, which is voltage 2, is induced by current I1. Also, V1 will therefore be equal to MdI2, as you can see here. MdI2 dt is going to be our V1 because V1 will be induced by current I2. Hence, this particular polarity that we have here. Please, this is very important. Don't make mistakes because you have to understand this. Okay, M12. This is going to be M21. This is M12. M12 and M21 are the same, so we can just say they are M's and then we'll let them go. All right. So how do we then write the voltage equation for these two loops that we have here? If you carry out KVL at the left circuit, this left circuit here, how do we carry out KVL? Let's go. VG, we have minus VG here because, you know, we are going clockwise. So we have minus VG plus the current passing through R1 is I1. So you have I1, R1 here. So we got this right. Let me pick. We have this, we have this. What about L1 now? Now we are dealing with voltage, all right? So you can see L1, we are coming this way, all right? So what we would have here is going to be this L1 di dt, and then for our current we have M di2 dt. This is very important. Okay, this is voltage V equal to L1 di dt because we are entering through positive, and for the voltage induced by current I2, you would have minus because we are entering that one, it is minus the I2 dt. So you have plus L1 di dt minus M di2 dt equal to 0. I need to be sure that you understand this. So I want you to please do me a message, send me a chat and let me know, send me a chat in the chat section, let me know you understand KVL for this left-hand circuit. If you don't understand it, I can go over it again. Don't forget KVL in a loop, you have to add, when you add everything together, when you do the analysis, you equate everything to 0. Once you miss it now, it's going to be difficult for you to solve many more problems as we move on. All right, so once we go to left-hand loop and we apply KVL, we are going clockwise, so we are traversing from negative to positive, so this becomes minus VG, right? The current passing through R1 is I1, so the voltage across R1 will be, using Ohm's law, would be I1 R1, so plus I1 R1. All right, now this is V, the voltage of these inductance based on the self-inductance. Voltage induced on L1 based on self-inductance will be L1 di I1 dt. So that voltage, we are traversing from positive to negative, that becomes plus L1 di I1 dt. All right, then voltage, there's another voltage here called M di I2 dt. This is the voltage induced on this inductor based on this mutual inductance, and this voltage is depending on current I2. It is induced by current I2. That is why we have M di I2 dt here. And the current passing through here is actually traversing through that voltage from negative to positive because we defined our polarities already. So this voltage then becomes minus M di I2 dt. That's why this is M di I2 dt, and then you equate everything to 0. All right. So let's take it a step for that. The same thing is what we're going to do for. The same thing is what we are going to do. Thank you, Davish. The same thing is what we are going to do for the right-hand loop. Okay, we're going to apply KVL to the right-hand circuit here. All right. What you will find out here is we're starting from R2. So we are going this way. We have I2 multiplied by R2. All right. So we have I2 R2, and then plus. Now, you will realize that we are traversing from positive to negative right now of the self-inductance on this L2 inductance. Okay, so this self-inductance, voltage induced by self-inductance on L2 is L2 di I2 dt. So you have plus, and the current here is traversing from positive to negative, so you have plus L2 di I2 dt. Again, there's another voltage here. This voltage is induced on L2 based on the current I1. So we have M di I1 dt. And this current I2 is traversing this voltage from negative to positive. That is why we have minus M di1 dt. And when you add everything together according to KVL, Kirchhoff's voltage law, you must equate them to zero. All right. So this is how we got these two equations here. They are very important equations. You don't need to memorize them. You don't need to memorize them at all, as important as they are. All you need to do is to be able to create them for unique circuits that will be given to you, different kind of circuits or problems or questions you'll be expected to solve. You should be able to create unique equations based on the parameters given to you in those circuits. So we have an example here, and then I think we should try to solve this example together and see how we can apply the concepts we just learned from the previous slides. So what we're looking for, write a mesh equation or write mesh equations for the above circuit with magnetically coupled coils. Write mesh equation for the above circuit with magnetically coupled coil. You can see we have a coil. This is, you can label this one coil. You can label this the second coil here. We have a current source here. This is we have a resistor here, another resistor here, and then there'll be mutual inductance here. All right. So the first thing you want to do is you want to define your polarities before you start anything. Otherwise, you might get it messed up along the line. So first of all, we have current. This is current I1, right, coming through this point here. So this is I1. So you can label this your plus. All right. If this is your plus, that simply means that this particular side here would be your negative. For self-inductance, so this is going to be like this. So for this is going to be L1 di2, L1 di1 dt. That's what it's going to mean, because this is going to be voltage based on self-inductance here. Now, voltage that will be based on mutual inductance will now be, this place will be negative and then this will be positive here. Okay, the rules are the same and like this. Okay, you don't have to memorize it. This place will be negative, this place will be positive, and I'm going to explain why. I don't even need to explain why. This is straightforward, but I've already explained it in the previous slide. Also, what you will find out here is that this current, I told you that wherever the current is entering the inductor from is usually defined as positive. That was what the first thing I told you guys when we started. So this place is going to be positive here, all right? And then this place is going to be negative. Now, this is going to be self-inductance for this particular I2. This is L2, all right, second inductance. So this is going to be the self-inductance here, all right? Now, what would be the mutual inductance for both of them? This place automatically becomes negative, and this place becomes positive for the mutual inductance here, all right? So you can label this place your mutual inductance M, and label this place your mutual inductance M. Since both of them are the same, this is going to be, so this is, if we refer to this as the first inductor, so this is going to be V1. There's going to be V1. So V1, as we know, will be equal to M12, right? Di2 dt. So here, if this is our second inductance, if we define it as a second inductance, this is going to be V2. Okay, so V2 will be equal to M21 di1 dt, because V2 is always related to the current in L1, while V1 is also always related to the current in L2. Good. So this is how it's going to be, and we know M12 will be M21, and then both of them will be equal to M. They mean the same thing. They will be equal to N. They mean the same thing. All right. So let's go on. I'm going to clean this up now because we don't need to memorize this. We don't need to cram it. All right. So we have this M here. Now they already gave us the value of the mutual inductance, right? What is the value of the mutual inductance? They gave it to us as 8. All right, so we know the value of the mutual inductance as 8. Everything is set for us to work with right now. We can then go ahead and begin to try to solve this particular problem. So in the first mesh that we have, this is what we are going to have. You would see that we have, where is my pen? You will see that here current is going this way in the first mesh. So this is going to be plus because we are dealing with this first. This is the self-inductance, this 4. So it would be 4 di I1 dt, because this is self-inductance. So it will be this is the inductance multiplied by the current passing through it, which is I1. So we have 4 di I1 dt here. Plus, there's another voltage here because we are carrying out KVL. There's another voltage here, which is going to be the voltage based on this mutual inductance. The first one is the voltage based on self-inductance. The second one is the voltage based on mutual inductance. And you do know that for our mutual inductance, all right, this is going to be plus 8D. All right, now for this mutual inductance, what is the current passing through 16 Henry? Because don't forget that we are saying that this mutual inductance for L1 will be based on current passing through this L2. The current passing through L2 will be IG is going this way, I2 is going this way. So I2 is going up, as you can see. I2 is going up here, and then IG is coming down here. All right. So the current passing through 16 Henry will be IG minus I2. All right. So it is it's going to now be the IG minus I2 multiplied by this 8, which is the mutual inductance that we do have here. This is very, very important. Okay, so IG minus I2, we do have that, and you will notice that IG is entering through this positive side. Okay, so that is why we have IG minus I2 there, and then this sign here determines the sign here. This is very important. So that is why this is going to be positive here. Also, we go ahead and say we have 20I. The current passing through 20 ohms will be I1 minus I2, because I2 is like this, I1 is like this. You still remember all our notations. So we have I1 minus I2 multiplied by 20 will give us the voltage across 20 ohms. Then plus the current continues here. IG goes this way, and then you see that I1 goes this way. So this becomes I1 minus IG, because I1 will take precedence here. So I1 minus IG multiplied by 5 gives us the voltage passing through this 5. Add everything together, it gives us 0. Now for KVL at mesh 2, this is our mesh 2. We want to find KVL here. So let's start with the area. Okay, our current is flowing this way, so it's traversing from positive to negative. For self-inductance, we have these 16 multiplied by current passing through each. 16 inductance multiplied 16 Henry, which is in inductance for L2, multiplied by the current passing through L2. So that is the self-inductance voltage. Okay, so that will be 16 multiplied by I2 will be given precedence here, so it becomes I2 minus IG, because we are in loop 2. So the current passing through that will become I2 minus IG multiplied I2 minus IG, so it becomes the I2 minus IG dt multiplied by 16 Henry. Okay, then again we have to deal with the mutual inductance. Okay, the mutual inductance. Don't forget that the mutual inductance here, this M, will be determined by the flow of current passing through 1. Mutual inductance in L2 will be determined by the flow of current passing through L1. The other time we said mutual inductance in L1 is determined by the flow of current passing through L2. All right. So the flow of current passing through M1 will be I1 is passing through negative M, isn't it? I1 is just going to be I1. So I1 passing through M. So it's going to be mutual inductance is 8 for both of them, but the polarity now will be determined by this current passing through here. So it becomes minus 8 di I1 dt. The rest is just going to be 20 multiplied by I2 minus I1 plus there is 60 somewhere here. It's going to be multiplied by just I2 passing through 60. We have that here. 20 multiplied by this I2 is going this way, I1 is this way, I2 is given precedence, so it becomes I2 minus I1 multiplied by 20. We have this. You add everything together, that gives you 0. So that is going to be the KVL at loop 2, basically. All right.